Okay, so in this one we're going to do numerical differentiation. Let me just remind you that what is the definition of a derivative? F prime of x is actually, let me do f prime of a, that's typically what happens here, is going to be the limit as h goes to 0. And of course I'll run this code so you can see what it says in just a second. By the way, this is LaTeX, which we're going to be doing shortly. Next unit, f of a plus h minus f of a over h. This is not working. Oh, I need to put a... There we go. So this is the definition of limit. If the limit exists, then we say the function is differentiable at a, and its derivative is equal to whatever that limit is. If we only look at positive values of a, we call this the right-hand derivative. If we only look at negative values of a, we call it the left-hand derivative. Sometimes the right-hand limit will exist and the left-hand limit will exist and they're not equal. Then overall the function is not differentiable, but we might say its right-hand limit, it's differentiable from the right and differentiable from the left. In this class, we're only going to look at functions that are differentiable everywhere, and so that won't be an issue. Or sorry, in this class, for the project, you can assume that the function that you will be passed is going to be differentiable everywhere. So even something like the absolute value of x, you're not going to have to deal with that at 0. Okay, so now how can we do something similar? How can we kind of use an idea like this, or how can we do a numerical version of this derivative? Well, again, we have some function up here. I'll use the same function. I'm just going to make it x squared for now. Whoops. Oh, return. Sorry. Okay. So what we want to do then is we basically want to approximate this difference quotient for smaller and smaller values of h. And how do we know how small we need to take it? Well, again, it's going to be this tolerance thing. Once two successive approximations are within some tolerance of each other, we're going to stop. So I'm going to have tolerance is equal to 0.1. I'm going to do 0.1 again. And then I'm going to say current derivative, or I'm going to say current dq for current difference quotient. Sorry, I need to give a value of h. So h is going to be equal to, I'll say 1. So current difference quotient, I've got fun is going to be fun. Oh, a, we'll do the derivative at a is equal to 2. Sorry. Fun of a plus h minus fun of a divided by h. Okay, now for this is going to give this is the slope of the secant line. Going between the points corresponding to x equals a and y equals a squared, and x equals a plus h and y equals a plus h squared. I'm saying a squared because that's our function. And let me just copy this down here so we can refer to it. Okay, so I'm just going to print this out. Print current difference quotient, and we're going to get 5. Now we're doing the derivative of x squared at a is equal to 2, so the derivative of the function is 2x, and if we evaluate this at a is equal to 2, we should get 4. So as I make a smaller, as h gets smaller and smaller and smaller, I should be getting something that goes closer and closer to 4, and it looks like that's exactly what I'm getting. Okay. Okay, so now what I'm going to do is I'm going to have a loop, and I'm going to compute the difference quotient as long as the difference between the successive approximations is bigger than tolerance. So I'm going to start difference is equal to 2 times tolerance, just to make sure we'll be able to do the loop. And now I'm going to say while difference is bigger than tolerance, dq is equal, h is equal to h over 2. So I'm dividing h by 2, so h is now going to be half of what it was before. But again, I can do divide equals 2. Whoops, h divide equals 2. Now dq is going to be equal to, well, this again. And then diff is going to be equal to numpy, that absolute value, dq minus current dq. Okay, and then current dq is equal to dq. Okay, so now what's going to happen if the difference is bigger than tolerance, it's going to do this loop again. And at the end, we're going to print the difference quotient. That is going to be the best approximation. So now I have the tolerance set to 0.1. So I'm going to run this. Okay. Whoops. Should be a minus sign there. There we go. Okay, so 0.04. That's definitely within 0.1 of the answer. So if I do 0.001 and run this code, we're going to get something even better, and so on and so forth. We keep getting something better and better and better, better and better approximation. Okay, so I think that's all that I want to say about this, except one thing that I do want to mention is we should vectorize this. So vfun is equal to numpy dot vectorize fun, and so here we should really have vfun, the vectorized version. If I run this again, I get that, and okay. So I'm not sure why it looks like the approximation is better than it was when tolerance is... Oh, so I just realized what's happening here is I did not set a starting value of h up here. Well, I think I had one, then I must have deleted it. Again, this is where Python, or this is where Jupyter can really cause problems, because every time I run this, it's getting closer and closer to 4, and it didn't make any sense to me, but it's because it's starting with the old value of h, which is already pretty small. So let me come up here and say h is equal to 1. And now when I run this, I should get the same. Okay. All right. Sorry about that. That was confusing me for a little bit. Okay. But there's a warning that you can take there. There's a mistake that I made there. Again, I'm going to blame it on Jupyter. I like Jupyter, but that was one of the weird things about that Jupyter can cause. Okay. So that's it. I think that's all of the instructional videos that I want to have this week. All I'm going to have one more video is just going to be talking about the project and what I expect for the project and kind of what you should do. Remember from the introduction video to the week, don't get too freaked out about the word project. All it means is just a slightly longer homework assignment.